mathematics solve such a
Proof, set theory, and logic review day. How's everyone doing? Doing good? All right. Next time is the exam. Quick note, I think I said this before, but just so everyone remembers, at the exam next time, for those of you in person, I will not be here. Someone else will be proctoring it. I will be out of town driving. And so yeah, so pretty easy day to have me not be here, since I'll just be I would usually just be sitting in the front of the room doing effectively nothing while you write. But yeah, so you'll come in, grab the exams, you'll have your time to do the exams, you'll turn them in, easy enough. It shouldn't really interrupt anything in terms of how the exam runs. Today is our review day, so I will answer any questions that you have. Before we do, I will take a moment to talk to the online students, pointing at the webcam in the back of the room. So for online students, the exam will be proctored online. To those of you who have reached out to me about how exactly this will work, I apologize for the delay in responding. I am attempting to set up the exam using HonorLock, which I have not actually ended up using before in another class. I've heard it's good. It comes with Blackboard. So I will send instructions about how that will all work. Basically, you'll just do the exam like normal, but you'll have your webcam on, so I can see that you're not, just Googling every answer or having ChatGPT do the whole thing for you. So yeah, it should be pretty easy. I'll send an announcement about that later today, and you'll get to see how it works. If there's any problems, I have a backup method, which is called the honor system, but I hope I don't have to go to that. Yeah, so cool. For people in class, it'll be the regular old way. Please don't cheat in class. That is always a no fun situation to put a guest proctor in where they have to be like, so-and-so cheated, and then, get themselves involved in it. I don't want to create work for them. Obviously, I don't expect any of you will cheat, but please don't, right? Okay, cool. So the exam, I actually have a copy of it here. Bum, bum, bum. It should be easy enough. Now I say that, of course, knowing that as soon as I say an exam should be easy, it effectively probably means basically nothing to you guys. Either that means that it is actually easy or that it's hard and I just think it should be easy for you, right? But it's not like a huge number of problems. That is, you should have a little less than let me think. You got like 8 or 9 problems over 50 minutes. So you got more than 5 minutes per problem, right? Not too bad. And some of the problems definitely won't require that long. Some of them are pretty straightforward. There's a number of multiple choice. There's some true falses at the beginning. Then there's some longer ones where you have to actually write stuff out. And we got our first question. What do we got?
Is it kind of similar to the homework?
Yes, quite. Yes. The question is if it's similar to the homework, and the answer is it is very similar to the homework. Yes. Yes. Do you get the rules of inference? No. You should know them. Yes, that is part of what you should know. And that is actually something that will come up. So I highly recommend knowing the rules of inference. I will not, I've not tried to make sure that the rules of inference are completely tested. That is, I haven't set this exam up so that everything that we've gone over in this entire first part of class appears somewhere in some problem. So that is don't go into it being I have to use every single one of the rules of inference. There are a number of problems where you have to show that a propositional argument is valid, where you take some premises, some hypotheses, and you derive the conclusion. And you go through this structured line by line of going hypothesis, modus tollens, 1 and 2, or so on, right? So you will use them, but I haven't set it up so that there's a propositional argument where you use every rule of inference in one of them or something like that. There may be rules of inference you end up not using, but I won't tell you which ones. So you need to know them all, right? There's not too many of them at the end of the day. So yeah, structure of the exam, pretty straightforward. Starts out with some true-false questions. Not too bad. The kind of thing where you don't really need to do any actual showing of your work. You can just kind of think it through. You could, I left like a little room to kind of like sketch a couple things if you need to kind of check your work a little bit, but most of it should just be checking kind of more basic stuff. Then there's a few multiple choice questions after that. Multiple choice questions, always nice, a little bit easier. Those ones you may want to actually show some work on. It's always a good thing to show work. I can give you partial credit if you show your work. If you just give me a wrong answer to a multiple choice question, I have little that I can do. And then after that, there are the non-multiple choice questions where obviously, of course, you have to show some type of work. Otherwise, what would I even be grading, right? And so these ones primarily fall into either some form of a proof. After all, this is a proofs class, right? So either showing that a propositional argument is valid, like we just talked about, one of these kind of classic ones there, or perhaps giving a proof of a statement. And I will tell you effectively how to prove it. I will say something like, give a direct proof, or use induction, something like that, to answer the question that I'm sure many people have in their minds. Yes, of course, there will be an induction proof. It won't be terrible, but I recommend that you look back over induction proofs. That's where I expect if anyone gets tripped up, it would be there. I have not made it a induction proof that requires the recognition of any sort of weird trick. That is, there's no thing where you go like, oh, okay, so I have like, k to the 2k plus 1, and this is equal to k to the 2k plus k, which is equal to, something like, right? No like weird one where you have to expand out like the k as like k to 2k plus, k plus, or like plus 1 plus plus 1, like k times or something like that. None of that stuff. None of these like weird ones where you need a fancy trick. All of them should hopefully be relatively straightforward, like breaking up a summation, something like that. The whole point is to see that you understand how to do the process of induction, not that you can happen to spot some sort of like a, finicky trick in a particular problem. And that's basically what the exam is all about. A couple of proofs, or showing arguments are valid, which I guess constitutes a proof as well, and a few multiple choice questions. You can imagine that the multiple choice and true and false stuff will be more about the things from the first little bit of the class. Stuff like, understanding a quantified statement, taking something written in plain English and turning it into a quantified statement, or turning it into some sort of, like writing it symbolically. Understanding like what is a tautology? Is something a tautology? I won't make you like write out big old truth tables, but I will effectively ask you things that you could answer by understanding the principles involved in constructing a truth table. That is, knowing things about, for instance, like when is an implication false? Right? Like when is P implies Q false? Stuff like that. And then you can use this fact to answer a question. So these would be what you would expect in like the multiple choice or something like that. Is something logically equivalent to another statement? Stuff like this. What do you think? Does it sound doable? All right, good. Now what questions do people have? What parts of what we've gone over so far are you wondering about or starting to struggle with or feeling concerned about? Yeah.
So would the best review just be like the homework assignments?
Would the best review be the homework assignments? Yes, definitely. If you feel like you understand all the problems on the homework, the exam will be, I don't want to say it'll be a breeze, but it will be easy enough, pretty straightforward. By the way, note to everybody, the clock is gone. The clock that is always wrong has been taken. Who took it? I don't know. It's on the ground. It fell off the wall. It's more wrong than ever before. All right. And it's upside down now. All right. But yeah, good question. Right on. Homeworks are the perfect thing to do to prepare. What else we got?
Are there any practice problems that we can do, like for the test?
Any practice problems?
Yeah.
I have not prepared like a list of practice problems explicitly. You can always go through examples in the textbook or the problems in the textbook, homework assignments, worked out solutions there. I I would primarily focus on that over just trying to like if you understand it, you don't probably need to just grind a bunch more problems out. If that makes you feel more comfortable, then just pick a type of problem and Google it. I mean, I could, compile a list of additional problems for you. But what I found is that people will then end up confusing themselves about those problems and then want like answer keys for those problems, and then it just turns into like effectively I've just created yet another homework key covering exactly the same material but with like tiny variations. Which I suppose isn't a bad thing. I could do that if people want, though it's a little bit late. The hour is late now for it, but yeah, instead of just grinding a ton of problems, I would focus on going back through what we've already done and making sure you really get it. Cool? Right on. What other questions do we have? Yeah.
When you like do problems that are like stacked and you derive the conclusion, can you ever use like T-Morgan's laws as like a justification for a step?
Okay, so the question is when we're verifying that a propositional argument is valid, that is, we've got like a stack of hypotheses, then something, therefore, conclusion, right? Can we ever use De Morgan's laws to claim that a step is valid? Yes. Totally reasonable. Absolutely a reasonable thing to do. So for instance, like you could have like, like step 1, something by hypothesis. Step 2, something by hypothesis. Step 3, doing something involving step 2. You could be like De Morgan's step 2, right? That's a totally reasonable thing. Yeah, absolutely. Or you could reference other proved results or proven results from class like this. Like you could say, like, for something disjunctive form of 1, right? Like if you're rewriting an implication as a disjunction, that's a perfectly reasonable thing to do. Yeah, totally fine. Basically, the goal of the justification steps is to break down the more complicated argument into simpler things that we have already shown effectively, right? That way there's no part of your argument that just is you being like, dude, trust me, or like, I mean, obviously, right? Like what you want is something that can be rigorously verified at every single step. And hopefully we've already done so. Cool? All right, nice, nice. Good question, fantastic. That's the kind of stuff that I'm talking about. What other things do we got? Yeah.
Do you recommend memorizing the universes, like natural numbers, real numbers?
Oh, okay. So yeah. So that question is, should we memorize some of these classic name sets? Yeah, I would say that's perfectly reasonable. Let's go over them really quick right now. Okay. So we got the natural numbers. These are, for instance, 1, 2, 3, and so on. Then you've got z, the integers, i.e., we can start basically the same place. You got 0, 1, minus 1, minus 2, so on and so on, 2, and so on and so on. All of the whole counting numbers, positive and negative. All right. Fun aside, the natural numbers, there is an eternal and perpetual disagreement amongst all mathematicians about whether or not 0 is a natural number. And clearly there's obviously no right answer. We just are defining a set. What do you want to put in it? You can put whatever you want in there. In this class, we're predominantly going to say that the natural numbers start at 1, just because that's the convention your textbook takes. It is, however, in no way wrong to say it starts at 0. You just kind of have to be clear on this point because no one seems to be able to agree. Amazingly, after all of these centuries, millennia, I don't know. What's natural? Is 0 natural? Is it weird? Is it an unnatural number? Hard to say. But then we've also got Q the irrational numbers, Q for quotient, i.e. we got fractions. So I won't be able to write out the list of fractions. A over B for A and B, both integers. Cool. Nice. Okay, then we got the reals. R these are all of the decimal numbers, if you want to think of it like that, right? Like anything that you could write with a decimal after it, right? With potentially an infinite number of digits, right? You can have like, i.e. like 0, 4, 9/12, square root of 2, 0.333, repeating, pi, so on, right? All of the regular old numbers from algebra and calculus and all that stuff, right? Then, of course, we've got the complex numbers. I.e. A plus BI for A and B in the reals. Cool. Nice. There's other things we could talk about. Some people occasionally talk about the irrational numbers. Those are the real numbers that aren't rational, and people will occasionally use H to denote that. There's plenty of other ones. But these are the ones that I would expect basically for people to kind of know. That is, if I write something, say something like for all n in Blackboard n right here, I am, I guess, at this point expecting you to know that I mean for all natural numbers n. So it is good to know those, yes, definitely. If you want to know why this is Z, it's for Zahlen, which is German, I believe, for number. So there you go. Cool. Everything else seems relatively obvious, though. N for natural, Q for quotient, R for real, C for complex. The Germans just snuck one in. All right. Other questions we got?
Can we do an example of like a proof by induction?
Can we do an example of a proof by induction? We probably can. And I'm going to silence what I'm sure is a spam call coming in right now. Yes, potential spam. I don't know about you guys, but do you feel like the spam calls come in like waves? I've been getting so many of them. It's kind of nuts. So here, let's pull up a induction problem. Let's see. Well, I guess I can pull an induction problem from our notes. Let me see, did I do all of these? No, I did all of these ones that I was going to do. Here, you know what we'll do right now? Let me keep this fresh, keep it new. Let's pull a random induction problem right here. Let's do okay, here, let me write this down really fast. Here's a good one. Why is there this dead pen up here? I keep throwing away the same dead pen all the time, and it just ends up being more dead pens. Here. All right, here's a good induction one. Let's do it. So I just pulled a random one off of the internet since I don't want to use one of the exact same ones, and I don't want to make it too similar to what is on the exam, and I know I accidentally will do that if I just try to make up a formula off the top of my head. So, where did I put this? Oh, in my pocket. Here is an example. Prove via induction that the sum from I equals 1 to n of 1 over I times I plus 1 is equal to n over n plus 1. All right. Assuming I copied this down correctly, let's find out. So we'll find out with the base case, I'm sure. Proof. We proceed by induction. For the base case, oh, and I should say for all natural numbers n, just to be clear. This is not allowing some sort of fractional summation or some weird thing. So we take the base case of n equals 1. Observe that, well, our sum goes from I equals 1 to 1 of 1 over I times I plus 1. And this is equal to 1 over 1 times 1 plus 1, which is equal to, oh, here, I'll just write it like, I will write this as a very long equality right here so I don't run out of board space. This is 1 over 2. Yeah? Okay. And now notice this is equal to 1 over 1 plus 1, which is exactly what we want. Yeah? 1 over 1 plus 1. Yeah? If you wanted to be extremely clear, you could write this out as like n over n plus 1, and you could leave this here with like an n right there, just to make it clear, since we've already specified that n is 1 in this situation. So we've shown that the formula is indeed good. Do you like this? Now, I generally, personally, try not to do this when writing examples because I think it can confuse people to think that we've shown this statement is true for all n somehow. So I like to leave the n very specifically as 1 and then write it more like this, even perhaps potentially putting parentheses around it to make it very clear that it's in the form that we want. To make it clear that, like, this is where I plugged in the 1s. Does that make sense? What are you thinking? Some people giving me a look that says, I don't know about that. That is, I'm just writing this statement here with n equal to 1. I could just leave it in terms of n since I've already specified here that n is equal to 1. But what I'm doing very purposefully is replacing all of my n's with 1s in this statement I'm trying to show so nobody accidentally jumps in and goes, hey, we've shown the statement. We haven't yet. We've only shown it for one case, n equals to 1.
How does proof by induction differ from proof by cases?
Oh, how does proof by induction differ from proof by cases? So here's the difference. Here's proof by cases. Proof by cases says that if P implies Q or R, and Q implies S and R implies S, then P implies S. This is the argument of proof by cases. I think we went through in one of the homeworks and you showed this. That is, you showed that proof by cases is a valid proof strategy. Effectively, you want to show that something implies something else. And instead of showing that it shows it directly, you say, hey, this thing, well, it implies something or something else. There could be overlap between them, but most of the time we have it be two mutually exclusive, possibilities, right? Like either the number is even or the number is odd. If the number is even, then you get the result. And if the number is odd, you also get the result. Therefore, no matter whether it's even or odd, you get the result, right? This is proof by cases. Induction works like this. This is cases. This is induction. We say something like this. We say something like P of A, and then P of, or I'll say it like this. So you've got a predicate, P of X, yeah? And what you do is you say P of, let me just say A for some specific value. Then you have P of X implies p of, say, like x plus 1. Therefore, for all x greater than or equal to a, p of x. That is, maybe I should even be clear here that these are x's being in like the natural numbers or the integers or something like that. Basically, it says if you've got your first step and having the predicate implies the predicate at a value 1 larger, then starting from the first step, we get step number 2 and step number 3 and step number 4, basically, right? Does that make sense? So the arguments themselves differ in terms of how you would just present them as a propositional argument. But if you want to think about it in a different way, induction lets you do proof by cases in a situation where you have too many cases to actually list them all out. You could do an induction proof for something where you have only finitely many cases. It would just be, I mean, it might be a reasonable thing to do. Like if you wanted to say for, prove this statement instead of for all natural numbers n, say for natural numbers between 1 and 100. You might not want to write out all separate 100 cases, and you can show that instead the first one holds, and that having 1 gives you the next, and so certainly the first 100, you got them all. But you can even go further, and you can prove it for more cases than you could ever write down. You couldn't write a case for every single number, right? That's actually a really kind of deep question that you're getting at right there, is that induction is like proof by cases in a certain sense. Like it's like saying like, hey, here's like a case for each natural number, and I want to prove it for each one. And now we've created a little repeatable formula to do that. That is, we start from the first one, and then we repeatedly apply p of x implies p of x plus 1 until we get to the one we want to. Right? Induction, it's like a template to prove each of those cases. Does that make some sense? Okay, right on. Well, if we got the base case, now let's do the inductive step. So the result holds for n equals 1. I'll say for the inductive step, suppose the result holds for a value k greater than or equal to 1. We're not going to specify anything other than it's greater than or equal to the base case. And then I'm going to explicitly say what that means, i.e., let's assume that the sum from I equals 1 to k, 1 over I times I plus 1, is equal to k over k plus 1. Yeah? Then we show this implies the result for k plus 1 as well. I.e., we show that the sum from I equals 1 to k plus 1 of 1 over I times I plus 1 is equal to k plus 1 over k plus 1 plus 1. Cool? Now, every time we do an inductive step, we're going to have the same essential process, basically. What we're going to do is we're going to say, hey, we start with one side of the thing we want to show, and we do some manipulations to turn it into the other. The only way we're going to be able to achieve this is by using our inductive hypothesis, that is, this fact that we've assumed is true for k. So we'll use that at some point. We'll begin with one side, we'll manipulate it into the other. Okay, so to do so, observe that, well, we take the sum, say, from I equals 1 to k plus 1. of 1 over I times I plus 1. And what might we do? What would you do? Split it. Yeah, right on. We could take the sum from I equals 1 to k of 1 over I times I plus 1 plus, well, the last term of the summation. This will be 1 over k plus 1 times k plus 1 plus 1. That's the last term of the sum. Okay. Now this step, I feel like perhaps if someone is not following this step, they may not want to say so at this point, but you should. You should say it instead of saying it, instead of realizing it on the exam. All right, right on, good, brave, I love it. Someone said, yeah, all right. So here's what we got. Here's the idea of what's happening here. In as easy a way to write it as possible, if you had a1 plus a2 plus dot, 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 all the way down through an minus, or an plus an plus 1, would you agree that this is equal to? Well, I could write it as, say, like the sum from I equals 1 to k, or let me even keep these instead of n's, let me make them k's, just to make life easy. This is the sum from I equals 1 to k plus 1 of ai. That is, whenever you're doing a sum, you start at the bottom thing, and then you keep going up by 1 until you get to the top thing. It's just like if you ever write like any code, this is just a for loop, right? You're just incrementing the variable one time every time, this dummy variable I. Okay, would you agree that this right here is indeed equal to a1 plus a2 plus dot, 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 ak plus 1, even if I put a parenthesis around it? Yeah. Now, this little chunk, using exactly the same logic as we wrote that first sum, is in fact the worst summation symbol I've ever drawn. The sum from I equals 1 to k of ai plus ak plus 1. That is, the trick is just drawing parentheses, basically. Does that make some sense of what's going on there? Sweet. Good. I'm happy to hear that. Okay, because some people get, it's happened too many times. I've seen someone get tripped up by this and they don't say anything, and then when they finally see it, they go like, oh man, I was confused for so long for no reason. So good stuff. All right. So if that makes sense, then that's exactly what we're doing right here. We're just saying, hey, for summing up all the terms, you could sum up, well, the first chunk of them and then just leave the last one at the end and add it on later. So we know something about this sum. That is, this is right from our inductive hypothesis, so we can replace it with what we've assumed it's equal to in our hypothesis. This is k over k plus 1. K over k plus 1 plus 1 over k plus 1 times k plus 1 plus 1. Okay. Oh, I should have a parenthesis there. Now, I think I just need to get a common denominator, right? Seems like all I really need if I want to add together two fractions. So let's do it. Let's put them together. All right, so get a common denominator. Just multiply both sides here by, both the top and bottom, by k plus 2. So I got k times k plus 2 plus 1 all over k plus 1 times k plus 2. And now, zooming on over to the next board and changing the camera so that we can see it, all we have to do now is put this annoying string away and continue with a little bit of simplification, right? I get, all right, I have k squared plus 2k plus 1 over k plus 1 times k plus 2. And now notice, going back to the thing we want to show, which I will hop the camera back over to point out, which is that this sum is equal to k plus 1 over k plus 1 plus 1. That is k plus 1 over k plus 2. We want to get k plus 1 over k plus 2. So looking at what we have a k plus 2 on the bottom, something on top we want to cancel with this k plus 1 here, and hopefully just end up with the k plus 1 on top. All right, so let's factor the top out. Would you agree that k squared plus 2k plus 1 is equal to k plus 1 times k plus 1? Hey, look at that. We get a little bit of canceling action. And so I just end up with k plus 1 over k plus 2, which I could rewrite as k plus 1. And I'll even put it in parentheses to make it super clear that this is exactly what I wanted to show. That is, I have k plus 1 over k plus 1 plus 1. OK, so having the result for k implies the result for k plus 1. We have a base case. We have a machine that lets us take any step and get to the next step. So the base case is the first step. And we can just keep reapplying this little machine to keep climbing up the stairs, right? Make some sense? OK, cool. So we just end by saying, hence, by the principle of mathematical induction, the result holds for all natural numbers n. Cool. By the way, it is the principally with an LE on the end, not, as I very frequently say it's spelled, principal, like your principal at the school. Every time I see that, I always think of, like, by the principle of mathematical induction, and I imagine, like, like some sort of balding man in a suit who's in charge of mathematical induction in the universe, right? What do we got?
So like on the test, are you judging your spelling?
On the test, I am judging your spelling, not in your grade, but in like a personal way. I'm just kidding. I'm not judging your spelling. I don't care. I misspell things all the time. Here's a fun, amusing personal anecdote. When I was a little kid, we had like spelling workbooks in elementary school, right? They would like give you these workbooks, and like every week you would do like a new little lesson, with spelling stuff, right? You have your spelling test on Friday, and I just kind of realized that they like gave us these workbooks, but they did like the teacher didn't check them except like at like mid-semester or like the quarters or whatever it was, right? They didn't check them for a long period of time. So I just took my spelling workbook and I got it like on the first day, and I was just like, all right, I just threw it away. And then I was like, I don't know, I don't have it. And they like didn't know what to do. But I'm terrible at spelling. I kept doing this. And I remember I got in trouble. They were like, Bryce can't spell at all. He keeps throwing spelling workbooks away. I also just refused to learn my times tables. So I'm very bad at times tables and spelling. But, you don't need it to be a math professor, I guess. So that's fun. I'm not judging your spelling is the goal of that story. And also, you can just throw your spelling workbooks away if you want. You can just do stuff. So. What else do we got? Induction, pretty good. What about a direct proof? Let's try something like this. Here's an example. Let's do an easy one. Give a direct proof. Give a direct proof that the product of two rationals is rational. I would say instead of rationals, we'll say rational numbers. Okay, this should hopefully be pretty straightforward, but let's try it. Let's make sure we get the idea of what a direct proof is. So an indirect proof would show that the statement is true without, for instance, like directly constructing something that verifies the statement is true. For instance, you could do an indirect proof that, via like a contradiction or something like that. You could say like, suppose not, and then derive something false, and then you'd be like, so it has to be true. Yeah? Okay. In a direct proof, we don't do this. We just directly show the thing is true. So let's do that. Okay, proof. Let A and B be two rational numbers. By definition, there exist, I'll write it this way, NADA for numerator and denominator, and NBDB. I'll even say there exist, just to make it clear, integers, NADA and NBDB, such that A equals the numerator over the denominator, and B is equal to the numerator over the denominator. I could have just picked some other letters, but I'm trying to make it a little more intuitive so I don't have 6 different variables flying around in a confusing way. Feel okay? All right. So, observe that AB is then NA over DA times NB over DB, which is equal to NA NB over DA DB. Since NA NB is an integer, as is dA times dB, this shows that AB is equal to, I'll write it as like some, like a P over Q for some integers P and Q. That is, AB is rational, since a rational number is just something that can be written as the ratio of integers. Cool? Does that make sense as like a type of direct proof? I'm being perhaps overly pedantic in this proof. And there is, if you are wanting even more pedanticness, a kind of somewhat missing step where I say that since this is an integer and that's an integer, which maybe someone would say, like, how do you know the product of 2 integers is an integer? Which maybe we'd need to appeal to more basic results and more foundational things. But stuff like that is perfectly reasonable in a proof for you to go along with at this point. We haven't built up everything from first principles yet. We haven't constructed, like some set theoretic representation of the integers and then dealt with multiplication in that foundational way. So you don't have to prove some of those very basic things like that. But does that make sense, what I mean for like a direct proof? Okay, let's see. Let me think of another type of proof of that nature really quickly. Okay, here, let's try another one. What if we do, give a direct proof that, n squared is divisible by 3 whenever n is divisible by 3. How about that? This is actually also a really easy one, but just to double check the idea. What would someone do to start with? What would you do?
Like n equals 3 times k. Such that
Okay.
integer.
Suppose n is divisible by 3, i.e., suppose there exists an integer k such that n is equal to 3k. Then n squared, well, this is just n times n, which is 3k times 3k, which I will write now as 3 times 3k squared. So n squared is divisible by 3 as well. That is, I can write it as 3 times an integer. That would be like the short way of writing it. If you wanted to be go longer, you could say something like, instead of just saying, hey, so this is divisible by 3 as well, you would just write this part, and then you would perhaps say something along the lines of like, as 3k squared is an integer for any integer k, there exists an integer m such that n squared equals 3m. That is, n squared is divisible by 3. That would be the more like long form, technically correct way of writing it. That is, we're at first appealing to the definition of divisibility by 3, which says, hey, n is divisible by 3 if there's an integer k such that n is equal to 3k. And now we show that the same is true for n squared. That is, n squared is also equal to 3 times an integer. It's also sometimes okay to brush that last little step under the rug, but if you feel more comfortable having that sort of symmetry, cool. Direct proofs. All right. Yeah, what do we got?
With like a counterexample proof, how far besides just showing an example, a counterexample? Like what do you have to
Okay, so the question is, with a counterexample proof, how far do you have to go just besides showing the counterexample, or providing the counterexample? Providing the counterexample is effectively enough, though it is usually considered good form to explicitly demonstrate that it is indeed a counterexample. That is, if our claim was something along the lines of like, here, I'll write this on the other board now. Let's see. So if our claim was perhaps something like, if we had something like prove or disprove X, so some people got to get rolling. Yeah, basically, we're at time, but basically what you want to do is show that it actually is a counterexample. For instance, the easiest kind of thing I can think of would be like prove or disprove. Say like x plus 1 times x minus 2 is greater than or equal to 0 for all real numbers x. Then you'd be like, here's my disproof. You could say like, you'd be like, the result is false. Consider x equals, say, 0. That would work, right? But it would be polite to show that this actually is a counterexample. So you'd say something like, then show the statement is not true, right? So that's a good way of doing it, right? Okay, cool. Great questions. If you have more questions, send me emails. Let me know. Have a wonderful day. I will not see you on Friday. I will see you next week. Good luck on the exam.